Hi, I'm Nathan Van Velson. I'm a lead engineer in the Research and Development Group here at Advanced Cooling Technologies, and today I'm going to talk about one of the technologies we're developing in R&D called the two-phase thermal switch. So there's a lot of applications where variable conductance features are desired to maintain temperatures of components within certain windows. And one of those technologies are thermal switches. In general, thermal switches operate where they conduct heat very well when on and restrict heat flow when off. Our version of a thermal switch uses a sealed metallic bellows which contains a saturated working fluid similar to the inside of a heat pipe, with one end of the bellows fixed to the heat source and the other end of the bellows free to move. The end of the bellows is set a certain distance from a heat sink for ultimate heat rejection, and the way that operates is when heat is applied, vapor inside the bellows is vaporized, increases the saturation pressure inside the bellows until the bellows comes into contact with the heat sink, at which point the switch is on. So you have a disconnected heat path when the switch is off, when the vapor pressure corresponding to the vapor temperature of the fluid inside the bellows is less than a certain value, and above that value and above that temperature and vapor pressure, the bellows is in contact with the sink and the switch is on. So the temperature at which the bellows contacts the sink is a function of a few different variables, one being the vapor pressure of the fluid, and that's going to fall along the saturation curve for that particular fluid. The other is any exterior pressure. This could be inside a pressurized container, or it could be in the vacuum, for example, if it's being used on a spacecraft. And then the spring constant of the bellows, and then the initial distance between the sink and the bellows end cap of the bellows. And that's kind of illustrated here. It's basically a balance of forces on the end of the bellows that determines at what temperature the bellows comes in contact. And so again, we can have kind of two different modes of operation. A pure on-off thermal switch, if you can cut the power to your heat source and the temperature drops below that set point temperature, the bellows will disconnect and now you've broken your heat wink. It also can operate in a variable conductance mode through intermittent contact of the bellows with the end, with the heat sink. And that's desirable for situations where you may have a wildly varying heat sink temperature, but you don't want the temperature of your components to drop below a certain temperature. So this is kind of illustrated here. For example, if you have a thermal switch design with your set point at some value, normally your heat source is operating for a given heat sink at some temperature, but then if the heat sink is to drop, it can go arbitrarily low, and the heat, as long as you're applying some power, the heat source temperature won't drop below that set point temperature as the sink drops. And so there's different applications for the thermal switch. Some of the ones that we're looking at is the thermal management of different sensors that can exist in wildly varying thermal environments. Another application is the helping components on lunar rovers and landers survive the cold lunar night. And there's probably several other interesting applications for the thermal switch. If you'd like to learn more about the thermal switch or any of the other ACT's thermal technologies, take a look at our website. Thanks.